modeling of fracture and constitutive modeling of material. In this session, Dr. Kumar will present on the topic of fracture mechanic analysis. His insight into this crucial area of study will deepen our understanding of material behavior under stress, which has significant implication in engineering, design, and safety. Let's give a warm virtual welcome to Dr. Pavan Kumar Asurvijaya Kumar as he takes the stage. Dr. Kumar, the floor
So
is
much.
yours.
Thank you so much for your introduction. So, can I share my screen?
Yeah, I can see clear your presentation, sir.
Okay. Now, can you see it? Can you see the presentation?
Yeah, sir.
Okay, perfect. Thank you so much for your amazing introduction. And I'm really happy to be here today with you. So I was thinking what exactly to talk, and then I decided that I think it's best if I give a motivation for the students to let's say understand fracture mechanics a little bit, and then try to give a perspective which is called phase field methods, what it can do, and what we have been doing in our lab from last 5 6 years, let's say. So again, a warm welcome to all of you. So I am Pavan Kumar from Institute of Lightweight Design and Structural Biomechanics from Technical University of Vienna, which is in Austria. For those of you who don't know Austria, it's very close to Germany. It's below Germany, actually. So again, let's get started. So if you see this, this was a headline in 1919, 16th of January, which says there's a huge molasses tank that exploded. And because of this, 11 people dead and 50 people got hurt. And if you see what is the reason behind this, there was a small riveted joint in the bottom of the tank. And as you can see here, and then in this, there was the stress exceeding. And because of this, there's a small fracture that happened. And because of this, the whole catastrophic event took place. And I don't know if you know this. So this was basically the ship called Liberty ship. There was 1,500 ships that were built in 1946 for the World War II, and three of the ships actually broke into pieces like this, as I'm showing in the picture. And approximately 70% of all the ships that were built were kind of broken. So you can imagine how catastrophic this would be, right? And this is a first commercial aircraft with a square window. So now in 2024, we know that square window, how the stress concentration works. So of course, it's easy for all of us to guess what would have happened. This was the first commercial aircraft. It's not even, let's say, design or test experiments or something. So of course, because of the square windows, the stress concentration, you can already see there, and then there's a catastrophic event that happened, and of course, putting a lot of people in danger. So I don't know if you remember this. 1 year ago, exactly, almost similar in August, there was a Titan submersible which went inside the ocean to see the Titan, which was kind of sunk long time ago, and then it imploded. The reaction time of the implosion was actually less than 1 microsecond. That means in one microsecond, the Titan submersible imploded, and because of this, whoever was inside lost their lives. I think we know this very tragic story. So what am I trying to tell here? So if you don't detect the fracture, or if you don't design for fracture, the catastrophes that unfold later would be very, very, very bad for the people who are in that or associated with that, or to the structure itself. It's not only that the people's life are lost, these are equipments which cost billions of dollars, and all of them are also lost in the process, right? Okay, these are big stuff. It's fine. It doesn't affect my life. But these are some stuff which affects your day-to-day life as well. So I know for sure there are 115 participants here. Out of them, you for sure know somebody of your family, your friends, or at least somebody who have fractured their bone, right? Either due to some accident, they were walking in a wrong way, or something happened and then they also fractured the bone. There is a possibility that you're drinking coffee. For example, uh, this is a coffee cup I am drinking right now, and then there is a hot liquid inside this, right, which is the coffee itself. And then when you have some problems, if there's a small crack somewhere, there is a good possibility that this coffee cup breaks. Or you might have gone to a restaurant and then you just drop the cup of glass so that it breaks. It doesn't break, it shatters into pieces like this. Or people who are using spectacles uh, may also experience this someday. They just randomly sat on this or something and then immediately the spectacles break, right? So all of these are examples of fracture that you see in every day. I can go on giving more and more and more examples, but it gets the point, right? So uh where do we start? Like, so now we are in 2024. It says 2022, but it's fine. That's the latest version I have. After that, not much has been done. So what exactly has happened in the last 100 years? So the first analysis of fracture is done in 1898 by Kirsch, called stress concentration in a circular hole. I think you studied this in your bachelor curriculum, I guess. Uh, it was not very helpful because it's just very vague way of representing stress concentration. And then more generalized terms was done by Inglis in 1913, where he developed the same stress concentration for the elliptical holes. And the energy approach was the most helpful one, which is from the Griffith. But the problem is, you will see the problem in a while, that these kind of energy approach was we were not able to solve this problem. That's the problem. So the most useful one, which is even used right now in the industries today, is the stress intensity factor near the crack tip, which was developed by Irwin. And then in 1960, Barenblatt developed cohesive zone model, and then followed by a lot of people. For example, Erdogan, Beshant, who developed non-local continuum damage theory. And then later, so the whole phase field approach is based on the energy approach from Griffith. So I will go in that direction now. So in order to solve the Griffith's approach to fracture, Ambrosio and Tortorelli developed this something called free discontinuity problem, followed by Perling's on gradient enhanced damage, followed by variational methods to fracture. So again, a lot of people came in the middle. The final and the final formulation was given by Blaise Borden in 2000. So if you see this particular paper, it's called Numerical Experiments in Revisited Brittle Fracture. You see it here. From 2000, there are 2,300 citations that have been done only to this paper. So if you see the amount of papers that are published in phase field methods to fracture alone in 2024, it would be at least 5,000 papers. So in the last 20 years or 24 years, if you see the amount of papers that are published in this area, it would be at least 50,000 papers. So you can imagine how big of a research field this is. If I compute also the fracture mechanics in general, it would be 100,000 at least minimum, right? So what is this Griffith approach? Why is everybody in the last 20, 15 years are going crazy about Griffith's approach? Because Griffith is the first person, again, this was 100 years before, he said that cracks are basically manifestation at the microscopic level. So what is he trying to say here? So when you have a small body, you apply a load, then the first thing that happens is in the microscopic level, there is a small cracks are formed. And these cracks, if the load exceeds a certain things, these turns into new surfaces. So he hypothesized that the energy required to break the atoms at the microscopic level is exactly same as creating new surfaces. Okay, so to put it in a easy way, if you have a paper and if you want to break the paper like this, so what is really happening is the amount of energy required to break this paper is exactly same as the amount of energy required to create these new surfaces, right? So before it was very intact, let's say here. Now, if I want to create new surface, what am I trying to do? I am breaking this, so I created two new surfaces here. Can you see it, right? So this is the exact hypothesis he gave. So in terms of mathematics, it would be written as something like this. So I don't want you to worry too much about the mathematics. I will tell you what exactly is happening in the next slides. Okay, so what is our idea in 2024? So we want to create structures which are very strong, very stable, uh, or you can say something like this. I want to build a rocket. So you can see here the picture of Falcon Heavy. This is one of the pictures from Spain. It's called Cetas. And of course, this is my favorite car. I don't know what is yours, but I think in the engineering level, you will always say Porsche or something like this. But why I chose BMW 7 is because it's one of the strongest cars. It's one of the most reliable cars as well. And this is one of the beautiful structures of airport. What I want you to notice is look at the small tubes kind of holding the whole structure, right? And this is of course not aeroplane from the Airbus, which is which I think most of you either seen or traveled, right? So now our idea is to design and develop these kind of strong structures, right? What would you usually do? So what we say is, okay, this is again in the context of topology optimization. So what we would like to do, if we want to create such structures, doesn't matter if it's automotive or even a coffee cup or your glasses or whatever you see around you or your structure, the classroom you're sitting in, the computer you're working on, or the Zoom, how do you say, the screen which you are seeing, everything is again has to be designed by somebody, right? So when you see that, what usually mechanical engineers do is they have some initial design like this, and then they try to do a finite element model, and then they try to do an optimization model, then you can do a topology optimization, and so on and so forth, as you can see here. But if you see in this whole process, I marked with red three important stuff. One is the finite element model, validation run, and shape optimization, right? These three are the most important when it comes to analysis, right? So why are they important? In this context of fracture mechanics is because if you don't take care of the fracture mechanics in these finite element model or validation run or shape optimization, the final design will be fully flawed design. So the final design, even though it looks beautiful, it will break like this, right? So that's why we have to consider fracture mechanics in the design optimization, especially when we are trying to do a finite element model. Okay, now what happens? Let's go back to our Griffith's theory. So what is this phase field approach? So our idea here is I have a Griffith's energy, which basically says that the energy required to break the atoms is exactly same as the energy required to create new surfaces. But this is very hard to solve. So what I do, I try to approximate this with some function which looks like this. Again, I am not going into details. Of course, you can solve this one very easily and then under some conditions. You might ask, Pawan, yeah, come on. This is too much of mathematics. Why do I need to know this? And I'm not even interface field methods. So for this, what exactly phase field does is something like this. So I have a sharp crack. So all the cracks are always sharp, right? So what phase field method say is, look, if I have a very sharp crack, it's very hard for me to understand this. It's very hard for me to mathematically even, let's say, try to represent this in mathematical terms. So what I will do is I will try to diffuse it a little bit. it. What do I mean by this? On the right side here, you can see this, right? There's a sharp crack, but what I try to do is I try to make it very smooth so that it doesn't appear to be a sharp crack. So this is the idea of face field. So meaning, so coming to the paper which we had before, this is the sharp crack. Now I cannot represent this mathematically. It's very hard for me. So what I do is I create a surface, something like this, which kind of approximates this sharp crack. So again, this is an approximation, huh? So keep that in your mind. So the value of approximation, if it's 0, then it's completely fine. If it's 1, it's completely broken. In other literatures, you will see people telling opposite. So it's again exactly same. So meaning that some people prefer to use 0 as very good material, 1 is broken. And some other people want to use it as 0 is broken, 1 is not broken. So here I am going to say 0 is completely fine and 1 is completely broken. Okay. So to again motivate you to look into fracture in detail, I'm going to show some examples that we have been doing from a very long time. Let's say 3-4 years, I would say. So this is one of the examples from thermomechanical analysis. So if you see, this is a second Danilov-Iska problem. So here you can see from the graphs that we can actually represent the experiments very well. So the most important stuff when it comes to mechanical analysis is to be able uh, to see large deformations, right? So in the picture here on the left side, you can see that I am pulling a bar from the middle, so it doesn't really, it kind of snaps. And the second one in the B, you will see also a bar which is put a force. So in the beginning, it's fine, but then it goes to an unstable mode as well. In the third one, again, this is bending. And on the right side, you will see a huge deformation from the annular ring. You can imagine this like a spring as well, but it's not really a spring. It's called annular ring subjected to a line force. So this can be done. So you will see that this is kind of, we were able to replicate exactly as it is shown in the experiments. So again, I'm going to show you with the fracture how exactly it is going to happen. So the red ones are always face field. So if it's 1, that means completely broken. If it's the blue color, it means it's not broken. So finding experiments to compare is usually very hard. So I'm going to show you in the beginning, at least, I'm going to show you only few examples with only graphs. But in the later, when we come to composites, I will show you also the experimental results as well. Okay. So here I have a plate with a notch of a rubber, and then you can see that how the fracture develops here, how it breaks. And this is precisely can be represented by the face field model as well. On the right side, you have exactly same, but with a similar, with a different geometry, sorry, different material, which is basically aluminum. Okay. Now, what can we do to the real industry problem? Is it possible that can we already apply to the real industry? So this is why I'm presenting you an application in the photovoltaic panels. So here you see, I think most of you have seen the solar panel with the bus bar, right? And on the right side, you have a thermal camera. So the last one, this one is a broken one. So here you see a stress concentration. And now we want to simulate this. Is it possible for us to know when exactly this happens? And the answer to this is yes. So on the right side, again, this is done using the face field method. So you see that there's a small crack that started here in the first picture. And then that crack somehow propagates like this in the second picture. And because of this, if you see the temperature, because of this fracture, you see in the beginning, the temperature starts like this, and then the temperature is completely concentrated in one spot, which is exactly what we see here in the experiments or in the real scenario. Okay, again, here is some examples of similar stuff with the cylinder. So this was kind of done keeping in mind a huge pipelines. So if you have a hot water pipeline, this may happen to in your home as well. If there's a small crack, let's say, uh, which is starting, and then the whole stress concentration changes, and because of the crack, temperature also changes, right? So boring stuff. I'll take you to the more interesting stuff. What we can also do is a deflection of crack. What do I mean by this? So you have, let's say, a coffee cup, and then you see a small uh, crack which is going appearing to start. Now the question is this crack going to propagate or stay? This is the question you have to ask. So of course, fracture mechanics can answer you this question, but but more importantly, the next question would be, well, I know that in aircraft wing, this place is where my stress concentrations are higher. Is it possible for me to completely change the direction of the crack if it starts? If it doesn't start, I am happy. I'm very happy. But if it starts, is it possible for me to change the direction of the crack? So for this, people mostly use a functionally graded material. So FGM here means functionally graded materials. So you can see here that in the home, if it's a regular material, the crack propagation is something like this on the top. But in case of FGM, this crack is completely deflected. Well, you will say, come on, you already told here what is the cracks, like two cracks are there. So it's just matter of closing the cracks. So I'll give you another example as well. For example, this is a riveted joint. Riveted joints looks more or less like this. Now, in the homogeneous material, you see here called A3A1. So this is for the homogeneous material. This is where the cracks would usually start in such a riveted joints. But on the right side, if you're using the riveted joints with the FGM, you can see that you can completely avoid the middle section, and then you can move the crack propagation upward. You can also do this downwards, depending on how you want to design your component. So the basic idea is you can deflect the cracks as well. If you know where is the stress concentration, you can always say, fine, now I am going to deflect the crack wherever I want it to be as an engineer, right? Similar examples can be done also for a cylinder. So here on the top, you will see the regular crack propagation, but in the FGM, you can also deflect this. Okay, so this is the final topic. I would need another 2-3 minutes to finish it, I would say. So here is an example of fiber reinforced composites. So if you ask me what is fiber reinforced composites, it's basically a long fibers reinforced in a matrix. So this is called long fiber reinforced composites. So if you see aircrafts, 75% of the aircrafts by weight uh, is mostly fiber reinforced composites, or wind tunnels. Uh, these days, even bicycles are made with fiber reinforced composites. So if you see the transition from one metal to other metal, now we are completely moving into fiber reinforced composites. So that means it's very, very important for us to understand how the fracture propagation happens in the fiber reinforced composites, right? So I'm just giving you an idea. So here on the matrix 0, so the fibers are oriented like this. So if I apply a load, what happens? I will show you in the next slide. Uh, it's also possible that the fibers are oriented in a 45-degree manner like this, or 90-degree manner. Need not be only these, you can actually orient the fibers in any way you want. So you can have 0 degree or 25 or 62 or 89, whatever you want. Okay, so there are very less experiments because this is a very new material which is available to us. So I'm going to show you some results for the long reinforced composites. So here is exactly the crack propagation in the experiments. And you see here that with the phase field, you can actually model this very well as well. So again, here is a plate with a notch. And you can see here for the 0-degree fiber, this is the crack propagation from the experiments. And on the top, you will see the crack propagation from the phase field method. So you can also see here for 30-degree, 45-degree, and 60-degree. And if you measure the angle of this as well, it appears to be exactly 30 degrees, 45, and 60 degrees. So it's very, very, very well matches with the experiments, not only in terms of crack propagation, but also in terms of force displacement curves as well. So again, I have another example for you for a open hole tension. So you see this is the experimental results, and on the top you will see phase field methods. So you can also ask this question, Pawan, in the A, it's very different from B, right? Why are you showing us there's two cracks like this? It's because uh, in the experiments, if you load a little bit different, or if you load exactly symmetrically, the crack that would appear looks like A here. But because there are some small problems in the experiments, either it chooses a path like this, or it chooses the opposite path. So meaning this, it is also possible to have a crack which is going straight like this and on the top. So in the experiments, this is the problem. But in the numerics, we can actually say, no, this is again coming from the problem of geometry. So we can choose which one we want. And of course, only one of them, but we can simulate both of them. We can simulate all the scenarios where the fracture can happen. Whereas in the experiment, it's only one of those cases or one of those scenario which really occur, right? Like as shown in A and B. So again, we can go one step ahead and say, fine, we have only experimental results for this because it's too expensive. Can we simulate for other examples as well, other scenarios as well? And the answer is yes. So here I have for 30°, 45, 60, even minus 30, minus 45, or minus 60 as well. Okay. So again, here is an example of compact tension. So the experiment shown below is done here in Austria. It's from a group in Linz. So they provided with this results few days ago to us to see if it's possible for us to simulate. So this is the compact tension. So you have two holes and then you pull it up. And this is for a 0°. So you can see that we can simulate exactly as it is. And this is for a minus 45° like this, and we can also simulate this. And this is for a 90°. So in the experiments, if you see, there's only crack going up, but when we were talking, they told if you take, let's say, 5 samples in the experiments, that some cracks go up and some cracks go down. And in the numerical modeling, we can represent both of them together. See, we have both cracks going up and down, right? So this means to say that numerical model is very, very helpful. It can simulate very well the experimental reality as well. So we even tried to apply this to very huge models, which I am not going to show today. If you're interested, I can suggest you some papers which we wrote in the last few years to suggest this. And here is another example which numerical modeling can do. It's called size and shape effect. So for example, consider this. So you have done an experiment on, let's say, a 5x5 specimen. You pull it and then you know everything about it, how the crack propagation. Now, if I ask you, what happens if I change one of the dimensions? Instead of 5x5 millimeters, what happens if I give you 5x10 millimeter? Then you will say, yeah, you have to give me the specimen so that I can do it again. Now my question is, come on, for this, I have to waste my resources. I have to build a model for you. I have to cut. I have lots of wastage. I'm spending a lot of money on this. Is there any other way? And the answer is yes. Numerical modeling can do this for you, right? So here I'm going to show you examples. So here on the left side, you see 8x1. This is a sample. Now we want to simulate something like this. In the originally, it would look like this. What you can do is you can take a sample like this, 1x1, and you can scale it numerically. You're not really scaling it. This is just numerical tricks, I would say. You can also represent such a crack propagation. So on the here you can see this. You can also represent a same 1x1 for a bigger model like 1x8. So the moral of the story is this, that you do one experiment and give me this experiment. Keeping that in mind, I can simulate the numerical or how the fracture happens numerically for any other things you tell me to do. and I don't need to change anything. You just give me one result, I can tell you what happens on a lot of things with a shape, with a size. If it's 5 cross 5, if it's 10 cross 10, if it's 20 cross 20, it doesn't matter to me. So that's what shape and size effects are doing. Okay. And here are some of the references, and thank you so much for your attention. So if you have some question, I would be very happy to reply as well.
It's like Mr. or Dr. Asur say that if the participant have a question, you can
Uh-huh.
raise your hand and give a question to the Dr. Asur. If anybody want to ask something about the fractal mechanic analysis to Dr. Asur.
Everything is clear. So you understood either everything or you understood nothing, right? Are you shy to ask questions? Feel free, okay?
Maybe the first one it's from me.
Sure.
So the first question is what are the key factor that influence the correct propagation in material and how can this factor be accurately modeled in fracture mechanic analysis? Because we know that in real condition and simulation it's different, but we can choose the parameter so that real condition can be same with the simulation.
Yes. So to answer this question, I have to invoke Bashant here. So in his keynote, when he was when he was taking the Timoshenko medal, he told something like this. I may be a little paraphrasing. So he said, fracture mechanics with all its scaling and interdisciplinary branches is exactly same problem as the dimension of turbulence, which means to say that it's so huge that it's very hard to say what really happens. So to answer your question based on this, it depends on what parameter you're choosing, depends on what material. So for example, if it's a brittle material, you don't have to do much. For example, if you just choose the correct fracture energy, which is as you get in the experiments, you can very clearly, let's say, uh, compare with the experiments with the numerical model. But if you are talking about a ductile material, then the whole situation changes. So if you have a stable crack propagation, then it's very easy to, sorry, it's not very easy to compare with the experiments. But if you have something from unstable crack propagation, it's much easier for you to propagate. So the same way in the composites, for example, if you are using a criterion, let's say like Pook criterion or Hill criterion, it's very easy to represent the experimental results. But if you are not using them, if you want to do by, let's say, taking the energies into consideration, or GC is fracture energy into consideration, it might be very hard. So it really depends on what exactly you choose from. So lots of things goes on.
Thank you very much, sir. So the
No
next
problem.
question is how do residual stress such as those from manufacturing process affects the correct growth in plates? It's the question
Uh,
from the reviewer, Mrs. Lilia Susanti.
Okay. So it affects, of course. So there are lots of papers written on this approach as well. So any residual stresses you have, for example, my let's consider, let's say, an example of brittle material, let's say like iron. Now in this you have some residual stresses, and then you assume that my breaking, like my fracture happens at 200 megapascals, and because there's a residual stress here, it can happen at 150 or even 180, depending on how much residual stresses are. But in the fiber reinforced composites, the scenario is completely different. Now, it really depends if you have a stress concentration, sorry, if the residual stresses happens in the fibers or in the matrix. So if it happens in the fiber only in one direction of loading, when you have a fiber oriented exactly straight like this, let's say exactly straight like this, and then you load like this, then only the residual stresses affect you. But if you have a fibers like this and then you load like
Pakai
this,
strip ya? Iya,
stresses
pakai
doesn't really
timing.
matter much. But if you have a residual stresses coming from the matrix itself, then no matter what direction you are, now the residual stresses matters a lot to you. So again, depends from the material to material.
Okay, thank you very much. I think that's all for this session, the keynote session 5. Now we from all the committee will give certificate to the keynote speaker as a form of appreciation and pride in being able to collaborate to make this event a success. So we
Thank you.
have to take the documentation first, sir.
Okay, thank
So
you.
Okay, give us a big smile, please. 1, 2, 3. Chaka. Okay, thank you very much.
Thank you. You're muted. Are you speaking something?
okay, I'm so sorry.
It's okay.
So we're moving to the oral session 2. Thank you for your
Thank you.
insightful keynote section, Dr. Kumar. Now we
Thank
are
you.
ready to transition into parallel session 2, where our presenter will showcase their innovative research in smaller, interactive breakout rooms. Presenter, please proceed to your assigned breakout room as indicated by the organizing committee. This is this is your opportunity to engage with your audience, share your finding, and receive valuable feedback. For all participants, as you enter the breakout room, please make sure to rename yourself according to the format provided by the organizing committee. This will help us to facilitate discussion and ensure a smooth session. We encourage everyone to actively participate and engage with the presenter during this time. Just remember to return to the main room by 15:50 for the exciting winner announcement, where we will celebrate the outstanding achievement of our participant. Enjoy the session and let's make the most of this collaborative experience. Thank you very much. We'll see you at 15:50.